So we worked on morphing operations, as got already teased by Thomas yesterday. And in specific, we want to move away from the metro maps, but instead we have polygons which outline the reachable area inside of a metro system. So these are travel time maps, and what we draw are isochrones. How can I scroll? Okay, sorry. So for example, here you have, you're starting at the Bertha von Suttner Platz in Bonn, and you use the public transportation, and you want to travel for 15 minutes, and everything that you can reach within 15 minutes is contained inside of these polygons. And as we are in the public transportation network, these can be disconnected polygons. And as we already saw, metro maps are often schematized, and therefore we use schematized outline polygons to display these travel times. And this was a previous publication, and now we thought it's inside of the transportation network, due to the inherent schedule, there's a high variance in these travel times if you compare them over the course of a day. And we thought that it's quite interesting to have an animation on this change of the travel times. And so what we did here is we took this map, which is generated for its starting time at 10 o'clock in the morning. And then here you have the same polygon, but only starting 5 minutes later from the same location. And you can see that, for example, you can suddenly reach this area up here, but here are some areas which you cannot reach. And if you only have these two visualizations, it might not be this obvious where the changes occur. And what we did is we developed an algorithm that can create a morphing function. So these are intermediate polygons which are between those two, and you can actually animate them so that you can see the differences. And So what we want to do is actually we have our source polygon on the left-hand side for you, and the target polygon on the right-hand side. And we want to find an animation which preserves the schematization of our input polygon. So all the lines here should also be octilinear during all the animation. And our ideas for this, first of all, we simplified the problem, or we transformed the problem by moving from a polygon to a polyline. We did this by simply selecting cutting points in both polygon outlines, and then we actually have a line string for both isochrones. And the actual morph animation is then broken down to a pairwise movement from the vertices of one isochrone to the vertices of the other isochrone. And these should be consecutive, so these movements should not cross. And for the motion along these paths, we assume uniform motion, so the velocity of the vertex during the animation is the same at all time. Different vertices can have different velocities, but one vertex has a uniform velocity. And what we did is we defined 3 basic operations which can occur. So here you have the source polygon, or a section of it, and the target polygon. And the first operation is a matching operation. So if we have one line which is horizontal, and in the output, or in the second one we find a corresponding one, we can simply match them and move them onto each other. And then we have a delete and insert operation, which are actually symmetric operations, just looking from the other direction. And these insert new line segments which spawn from a single vertex. And as we assume uniform motion, during the transition, the orientation of this line segment will actually be kept, and we still have these octilinear movements. For the matches, we have to be a little bit careful, because if we match a segment which has a different orientation, segments of different orientations onto each other, then we change the orientation, so we cannot allow them. The issue with only using these three basic operations is that the point movement is not really, it can have strange results if we have different numbers of vertices in the different polylines. So it would look like this. So one segment is matched on the other, and all the other segments can only be deleted. And to circumvent this issue, we allow to insert additional vertices in so-called multi-operations. And for these multi-operations, we worked with different methods on how to select these auxiliary vertices. And in specific, we came up with three different methods. The first one is, for every vertex on this line string, we use the relative position. So this might be 20% of this whole line string. And then on the other line string, we also take the first 20% and insert a vertex there. The second one is, for every non-aligned segment on this line string, we take the midpoint and use this relative position on this another segment. And in the last case, we here have a chain of non-aligned segments, and we use the midpoint of this chain of segments. And where's my mouse? Okay. Again, we have some examples for this toy example here. So you can see we have three additional vertices, but actually in this toy example, only one of them is really needed, because this could just be one matching operation and the output would look the same. And if we now, maybe I can show them both at once. So these other methods, they generate less additional points. And as it can already be seen in this toy example, the quality of the morph is not changed much, but the running time of our algorithm is much better if we have less auxiliary points. So while we did not perform a quantitative analysis of this yet, just by qualitatively looking at examples, we figured that the last version might be sufficient. And okay, and now how do we decide which operations are actually good and which are bad? And for this, we need to quantify the quality of the morph. And here we have we applied different cost functions. And for now, actually, we started with a very naive one, that we wanted to maximize the number of matches, because we thought matches are better than the other two operations, but the results were not really good. And therefore, we used a geometric approach where we tried to minimize the distance a vertex has to move from one polyline to the other polyline. And we are able to minimize this traveled distance over the whole morphing operation by using a dynamic programming approach by Martin et al. And there we actually built up a table which contains all the cost functions and the accumulated costs. And by backtracking, we can find the optimal solution. And before I will go to future work, maybe I can show one more complicated example. So these are now two travel time maps, or two isochrones with different travel times. So not a different starting time, but different travel time. And so you can see that there are still some issues here. For example, in this area, the morphing operation actually moves inside of the inner polygon, which for this specific use case might not be really good, because you actually have more time in the intermediate morph steps, so they should not be smaller than the original one. But still, yeah, I think, yeah, the general, in general, the operation looks quite good already.
So blue are the matching?
Yes, exactly. Blue are matching operations. Red are delete operations, so these are actually present here and not present there anymore. And green is the other way around. They are present in the inner polygon but not present in the outer polygon. And if there's some more time, maybe this we try to add a background map. And I did not point this out maybe clearly enough, but these multi-operations, we need to limit them to a certain amount of segments which are allowed to be matched on a single segment. And in this example here, we chose this parameter too small, and therefore the number of segments which are on this outer polyline is too large to be completely matched on this segment here, and therefore these parts here which do not need to be morphed are still morphed just because there are no segments left to be matched. Yeah, so this is still work in progress. These are our current results, but yeah, I think it looks quite promising. Okay, yeah.
That's really cool. You mentioned that you have these two different, I think you have the various different morphing things, and for just having just one point, like just once up, once down, it looked quite sensible to use the fourth option.
Yeah.
Is it you judge the quality of the morph by these more complex ones, where you might have long chains of different orientations?
Yes. So as I said, for now we have not performed any quantitative analysis. We just did it visually, and so we did not really see large differences for using more points, which give more degree of freedom to the morph. Yeah.
So in this example, you see not only that the expanding shape moves into the inner shape, but it also intersects itself, right?
Yeah, exactly. So here, this is another issue right here. So we have self-intersections.
So do you have an idea already how what would be a viable approach to fix that?
Yeah, so our idea is actually to maybe use different cost functions, that we penalize transitions which would cause self-intersections. The problem with this is that the algorithm somehow depends, or if the cost function is harder to evaluate, then the whole algorithm gets a lot slower. And
can you do these transitions? Maybe you should compute some routing or so for these things to go.
Yeah, another idea would be to first maybe morph these pockets to disappear, and then have a second consecutive morph operation, which then morphs these more simple polygons into each other. This could also be an option. Yeah.
From both sides, you need
for example.
simple polygons in between.
This is a really hard to morph anyway, so maybe it's a good idea to simplify this first. Yeah.
How do you handle if a new disconnected component is added?
Oh, yeah. So maybe I should talk about this as well. So for now, we only consider the cases where we can match one. So our travel time map consists of many different polygons. And for now, we only consider the cases where we can clearly identify one polygon which needs to be mapped on one other polygon. So you can see that this is the case here also, and there at the bottom. But maybe if you take a little bit more travel time, this blue zone merges into one zone, and then you suddenly have two red polygons which need to be morphed into one blue polygon. And this is also something which we want to look into in more detail on how we can do this. And maybe for this, for now we only use the geometric outline as input, but we have the information of the public transportation network. So maybe we could incorporate this into the morph animation to get better results and also handle these cases. Yeah.
So if you think of the application where you maybe have a starting time at 10 o'clock and then at 10:05, if you interpolate like this, it looks like a continuous like space between the two. But in fact, in public transport, if the train is gone at 10:02, then somehow there's a discrete change happening. Suddenly you cannot reach something within 15 minutes anymore. You have to wait for the next train. So is this something that you can do with morphs, or is it just if you want to show these abrupt changes, then morph is just not the right thing to show it?
I'm actually not sure. I've thought about it as well. Yeah, maybe this is. Do you have an idea?
Yeah, I was also wondering that too. But it's like the morph, you cannot stop the morph halfway through the morph and claim that that's the reachability exactly between the two time steps, right? That's not the case.
Yeah.
So these are actually discrete changes that you have. So I think this is actually showing these discrete jumps.
I guess what you see here is maybe a bit exaggerated. I mean, you don't want like a pixel map and more of that, because the recomputed pixel map for every second, that's probably too slow. So you want to do this morphing, but I guess not on this scale, right? Maybe you just want to do much smaller morphs, so that it's efficient enough, but that you don't interpolate. Basically, so small that you can hardly see it. But that morphing it is more efficient than another solution, I guess.
Well, I mean, the animation is quite slow now, so that we can see what happens. But I think if you have if you maybe have a slider where you can pick like, okay, 15 minutes or 30 minutes or whatever, and then rather than just jumping to the other image, you do this animation in half a second, or in a second, and then it's got like floop, and then I think that will work very well to do the morph, to not confuse the visual information of where things came from.
So the user never consciously gets to look at the intermediate stages, which we are looking at now.
Not at this speed, I don't think.
Also, we're not allowed to swim in the Rhine. At least that's what they always
So actually the schematization done here is, if we don't have any information because there are no roads, then we can draw however we want to.
Okay, so with this, or did you want to show anything else?
No.
Okay, then with this public health information, I would like to thank Axel for his talk. And ask for the third speaker to come up.
Oh.
Maybe not recommended.
And for somebody else, that's up in the newspaper. At least it's in